Hello, and welcome to your 8-9 homework video lesson. In this lesson, we're going to be looking at how we can write sequence of transformation proofs, very similar to the sequence of virgin motion proofs that we had done earlier this year and you saw in preparing for your midterm. In order to write a sequence of transformation proofs, though, we do need to get some key details down. So remember from a couple of lessons ago, we were able to calculate our scale factor, the K value, from a dilation that took place. And just to recall, the K value was always calculated by finding the distance of the image to the center of dilation versus the distance of the pre-image to the center of dilation. So we always said image over pre-image. So we can calculate, in this example shown to the left, the scale factor of the dilation from triangle JKL to PQR. You want to make sure that you read carefully because they're saying to become triangle PQR. So they're giving us some clues here. JKL, this is the pre-image, where PQR would have to be the image if it's the result of a dilation from JKL. So you want to make sure that that's clear. And then to calculate the scale factor, you just have to choose a pair of corresponding sides. And as long as they're corresponding, it doesn't matter which combination of two that you choose. So I want to calculate my scale factor. It's image over pre-image. And I'm going to use the sides that I had highlighted in green to get that information. So my K value should be image is 6 over the corresponding pre-image is 4. So that becomes 3 over 2 for my K. We have the same diagram in our next example, however, now we took the numbers out. So we have to represent the scale factor using length and distance instead of values. So in order to calculate a scale factor here, I'm still going to set up a ratio. I still know that the pre-image is the image where I started, still triangle JKL. We haven't changed anything from the first problem, which means that our image is still triangle PQR. If I want to calculate the scale factor, it's still going to be image over pre-image. Except now, when I choose corresponding sides, there aren't numbers in place. It's just the values of the side length. So my scale factor can be represented as the two corresponding sides that I selected. So that would, in this case, would be QR over KL. I didn't have to choose those two sides. I could have just as well had gone with JL and PR here. If I want to represent my scale factor in that case, I would have written image PR over pre-image JL. So it's all about how you're seeing it and interpreting it. As long as you're picking corresponding sides and calculating scale factor with image over pre-image, you should be in good shape. So here's the plan. In this video, we will describe a similarity transformation sequence to prove that triangles are similar. We'll do this by showing that an image is congruent to a dilated version of a pre-image, thus making them similar. But first, what it means to describe is very important to make sure that you remember this because it's pretty important moving forward for the end of the unit. So when we're describing, we want you to see thorough responses. We would like to see details whenever you're describing a transformation taking place. You should be using full sentences and make sure it's always good form to write a conclusion once you're all done. So here's an example of a sequence of transformations. They want us to explain how triangle ABC is similar to triangle DEF. So if ABC is similar to DEF, I'll choose ABC to be the pre-image and DEF to be the image. So that way I know I'm moving this way to get triangle ABC to become DEF. So my game plan here is first what it looks like I'm going to have to do is translate. So remember, whenever you're talking about translations, you want to include vectors in your description. And then after I translate, I'm going to just have to dilate. And we'll talk about the details that you need for a dilation when we get to it in this proof. So to start the response, the sequence of transformations that will map triangle ABC onto DEF are first your translation. So we'll translate triangle ABC along vector. And this is where you just want to be clear. I'll do along vector B to E, just so that we're all being consistent across the board. You could have done C to F, A to D, but I like to match up two marked angles together. So along vector BE, remember vectors get symbols, so that side BC coincides with side EF. You can even sketch in where this triangle would land if it helps you see that not just BC will coincide with EF, but side BA will also coincide with side ED. This is our first time using this language of coincide. Why don't you get a highlighter out or underline this right now? When we talk about coincide, we're talking about sides that overlap. So these sides are overlapping each other, and that's our goal of the dilation, because now our final goal is to get AC to overlap DF, and the way we're going to have to do that is by a dilation. So in our second step, we're going to say that we dilate triangle ABC now, and the center of dilation is at point E or point B by a scale factor, another important detail, of your image over pre-image. So I'm going to choose DB, DE, over AB, so that our final two sides coincide, so that AC coincides DF. So because all sides are in proportions due to a common ratio or scale factor, both appropriate to say, the triangles are similar through SSS similar. So important details to include in a dilation proof is your center of dilation. It's the scale factor. Remember, image over pre-image is important. And this new terminology about coinciding sides. You should be okay. Just watch the video one more time and we'll check in tomorrow with a quiz on a rigid motion and transformation combination in a proof.